Okay, our last review video is going to be really short because we've just finished doing these two units, so I expect it to be fairly familiar to you, but just kind of reminding you of some things to be paying attention to. So we're talking about applications of integration beyond just the kind of general idea that integration of rate of change gives me total amount of change, looking at very specific integration applications including area, volume, and differential equations. As I've told you before, area volume is very, very likely to be on a free response question on the AP exam, and it's very geometric. You don't have to think quite so hard, so you want to make sure that you're really confident about area volume because it's an easy free response question to get lots of points on and to score well on. So, just some general review about area volume. Remember, area, we integrate from A to B of either top minus bottom if we're in terms of x, or right minus left if we're in terms of y. If I'm in terms of x, A and B are the x values of the points of intersection of the two curves. If I'm in terms of y, A and B are the y values of the points of intersection. So once you decide whether you're dx or dy, that drives everything. Top minus bottom, these are both functions of x, some f of x's. Right minus left, these are both functions of y, some f of y's. Meaning that the f of x's, x is the independent variable and it's in the function when you plug it in. F of y's, meaning that y is the independent variable and that y is the variable when it's plugged in. And I'm using f of y there very loosely just to remind you they may not all be functions, so don't get caught up on my notation of calling that f of. They may not be functions. Then remember our volume rules. The very first question we ask ourselves if we're doing a volume rotated about an axis is it disks or washers? In order to be disks, the area that's to be rotated must be flush with the axis of rotation. There can be no space between the area to be rotated and the axis of rotation. It has to be completely filled in. And then we're using the pi r squared volume, either dx or dy. If I'm going around the x-axis or any other horizontal line, I'm dx. If I'm going around the y-axis or any other vertical line, I'm dy. Washers are used when the area to be rotated does not lie flush with the axis of rotation, so that there's any space at all between that area and the axis of rotation. But then, and the washer formula, remember that you square separately. So you need squaring, the only time you square together is when you're describing a single length squared. If you're doing washers, you always square separately. And you always measure your radii from the axis of rotation. Not the x or y axis. Whatever it is you're rotating about, stand there and draw your radii out. And there's our formula for washers. So capital R is the function that forms the boundary furthest from the axis of rotation, and lowercase r is the inner boundary function. Remember, if I'm doing something like I have this graph, and I were rotating about the line up here, let's say that's y equals 2, then both of my radii, both my big one and my small one, would start with 2 minus, because this y equals 2, the axis of rotation where I'm measuring from, is above both the larger and the smaller radius. If I were rotating around x is 1, negative 1 over here, then my radii would start with function minus negative 1. So make sure that you're thinking about drawing from the axis of rotation, and then to describe those lengths, you're either thinking top minus bottom or right minus left. And then known cross-section, just remember your area formulas, and remember that you could be asked for things that are not one of these. So you might be asked for a rectangle, and you just start from the formula base times height and then try to get it all described in a single variable. You might be asked for a right triangle, and then remember 1/2 base times height and describe those, the length of the base and the length of the height. So you want to start from the concept rather than trying to memorize each individual formula. Differential equations, that's the chapter we just did, and some of you are reassessing on it now, and so you're still studying that. But the methods of solving algebraically, remember that's SICKY. Separate, integrate, solve for C, and put in y equals form if possible. If you see the directions, find the formula y equals f of x, that means you're supposed to put it in y equals form, so there's a way to do it. And then remember slope fields. The slope field is the graph of the solution. And slope fields graph all the possible solutions unless you're given some particular value of C, but you're seeing. That's it for our applications of integration. That's a really high-level overview, but again, we've just finished talking about these, and we'll see some in our multiple choice questions. These types of questions actually are more likely to show up in free response because they require a fair amount of algebraic work, both area, but volume particularly. Sometimes you see area multiple choice, but differential equations, other than very, very simple ones, you'll be seeing those in free response questions because there is so much work to be graded. All right, that's it, and we'll work on integration in tomorrow's class. Values of C there.